All right, this video is for learning target 6 and 7. In class, I'm going to break this up into a 2-day lesson, but for the video's sake, I wanted to go ahead and teach it all in one lesson and record it. So the first thing we did is a warm-up exercise to see what you remember from Algebra 1. So here we go. The square root of 144 is 12, because 12 times 12 would make 144. The square root of 144 is 12. Square root of 50 can be reduced by changing it to square root of 25 times 2, and the square root of 25 times the square root of 2. There's a rule that says you can break the square roots apart, and the reason we chose these numbers is for the next step. The square root of 25 is 5. So that turns into 5 times the square root of 2, or the answer is 5 square roots of 2. That one's the one that most people struggle to remember, reducing square roots. Number 3 is straight FOIL. You have two items times two other items. So you'll multiply b times 2b, which is 2b squared. You'll do b times negative 5a, which is negative 5ab. And then you'll distribute the 2a to the 2b and the 2a to the negative 5a. So the 2a times the 2b, 2a times the 2b, is a positive 4ab, and the 2a times the negative 5a, 2a times the negative 5a, gives you negative 10a squared. The two terms in the middle are usually like terms, as they are in this case. They're both ab's, so they become 2b squared. Negative 5ab plus 4ab is negative 1ab, and then minus 10a squared. So the middle two terms combine, but the other terms are not like terms. Again, these are Algebra 1 concepts, things that we should have picked up on in Algebra 1, distribute, combine like terms, and whatnot. We're just reviewing them because every concept that we use here in Algebra 1 are concepts that we're going to apply in Algebra 2 today with something new. Number 4, we'll notice there's a plus sign in the between the two parentheses. So while it looks a lot like number 3, it is different. You're adding them. So when you're adding, you just add the like terms. You can ignore the parentheses, and you add the b and the 2b to get 3b, and you add the 2a and the negative 5a to make negative 3a. Final answer. And then number 5, notice you are subtracting these two parentheses. So you will subtract them, b plus 2a, you will subtract the 2b, and you will subtract the negative 5a. But when you subtract a negative, it's the same thing as adding a positive. That's the one that most people mess up. When they distribute the negative to the negative 5, they forget to change it to plus. Then combine your like terms, b minus 2b and 2a plus 5a. I would put the a's together here first, 7a, and then b minus 2b would make minus 1b. So 7a minus b. If you write this as negative b plus 7a, that's fine too. Either one's fine. All right, then the last two. Quick reminder, in class I would have asked them, what could you square to make 6? And they would have all said probably 6. And then I would have reminded them that not only can you square 6 and get 36, you can also square a negative 6 and get 36. So keep that in mind over here on the left. When you're solving x squared equals 36, you're going to take the square root of both sides. The square root of x squared is x. But because there are two different things you could have squared to make 36, we're using the square root property over here. The square root of 36 is 6, but don't forget that the answer could have been positive 6 or negative 6. So you have two answers, plus or minus 6, positive 6 or negative 6. In number 7, before you can solve for y, before you can take that square root, you have to divide by negative 3. Isolate that y squared. So when you do, you get 40, let's see, I think you get 49. I'll have to, negative 147 divided by negative 3. Yeah, you get 49. So y squared equals 49. And when you take the square root, don't forget that there are two numbers that y could have been, 7 or negative 7. So plus or minus 7. Two answers. All right, that's the review. The new stuff has to do with the imaginary unit I. These are three concepts. One, two, three. Three concepts that we're going to explore throughout the next of the notes. Because until now you've been told you can't take the square root of a negative, you can't take the square root of a negative, there was this thing called I invented to take care of that situation because it comes up in places that they needed to address it, they needed to define it. So they defined the square root of a negative number to be I, the imaginary unit I. The imaginary unit I. And it's defined as the square root of negative 1. You can extrapolate from that I squared is negative 1. If you squared both sides of this first fact, I squared, so square the left side and square the square root of negative 1, you end up getting, well, the square root being squared would kind of cancel. So I squared equals negative 1. So anyways, the second fact is really part of a derivative of the original I equals the square root of negative 1. But anyways, we will use the I equals square root of negative 1 exclusively for reducing radicals, for reducing square roots. We'll use I squared equals negative 1 any other time. So if it's not a square root, we'll be using the second fact. And then the third fact, a complex number is anything in the form a plus bi. So for example, 2 plus 3i is a complex number. It has a real part, 2, and it has an imaginary part, 3i. All right, so now using these, we will simplify and solve radicals, products, equations, add and subtract, multiply and divide. We're going to do a lot of things algebraically to numbers involving these square roots that are negative and involving I. All right, the theme of today, and the theme of adding and subtracting, multiplying and dividing, the theme will be if your gut tells you that you should do this, it's probably what you should do. Like if algebra says you distribute, if algebra says you combine like terms, you're going to do the same thing with this imaginary unit I. All right, so quick little why are we looking at this and what is it? Remember yesterday when we did Learning Target 5, if we had a picture like this one, x squared plus 2x plus 3 equals 0, and it doesn't cross the x-axis, we would have said there is no solution. But actually, there's no real solution. There are two imaginary solutions, and they are negative 1 plus I squared to 2 and negative 1 minus I squared to 2. Something that we're not going to get into just yet, but I want you to see we're going to be using these to solve quadratics in later targets. Right now, we're just getting comfortable with the imaginary unit I. Okay? So that's going to be in later targets. Now, I've already talked about I being defined as the square root of negative 1. I've already talked about I squared being negative 1, so those are things I'm not going to talk about or read. But pure imaginary numbers is something I haven't talked about. They are 6i, negative 2i, or I squared to 3. They are any number that just have I with them. Complex numbers, we already talked about. A complex number is 2 plus 3i, but a pure imaginary number just has the 3i part, the imaginary part. All right, moving on. All right, in A, B, and C, we start to simplify square roots, radicals that are negative. In middle school, your middle school teacher would have told you, no, you can't do that. You can't simplify a square root that has a negative, excuse me, because that's not a real answer. Well, okay, your middle school teacher is right, but there is an answer. There is a reduced imaginary answer. And my Algebra 2 teacher taught it as poking the eyes out. Rewrite the square root of negative 25 as the square root of negative 1 times 25. We can break it apart as the square root of negative 1 times the square root of 25 and reduce both of these. We already knew the square root of 25 is 5. But now we know, because of a definition, this definition, the square root of negative 1 is I. So this is I times 5, or 5I, a pure imaginary number. Pure imaginary number. Answer for B, the square root of negative 8. 8 is not a perfect square. So when we rewrite 8, we'll first poke out the I, if you will, by rewriting negative 8 as negative 1 times. Now I'm thinking 8, 8, 8, 8. Is there a perfect square? By the way, the perfect squares, if you've forgotten, are 4, or 1, 4, 9, 16, 25, 36, 49, blah, blah, blah. Are any of those factors of 8? And yeah, the number 4 is a factor of 8. So I'll rewrite this as 4 times whatever's left, which would be 2. And I'll break it apart into square root of negative 1 times square root of 4 times square root of 2. And then reduce each. The square root of 4 is 2. The square root of negative 1 we just learned. It's defined as the letter I. And the square root of 2 can't be reduced, so it's the square root of 2. So the final answer, this is 2I square roots of 2, or you may see it written this way as 2 square roots of 2I. Just make sure if you write it the second way that that I is not under the square root. That's another pure imaginary number. All right, last example, C, the square root of negative 75 can be rewritten as the square root of, poke the I out, so square root of negative 1 times, let's see, what goes into 75? 75 is not a perfect square, but what goes into it that is a perfect square, that would be 25, and the leftover 3. So if I rewrite that as square root of negative 1 times square root of 25 times square root of 3, the first is I, the square root of 25 is 5, and square root of 3 does not reduce. So this is 5I square roots of 3, or 5 square roots of 3 times I. Either answer. All right, now this is your turn. Check your progress. I'm going to pause the video. If you're working this at home, pause it. Try these 3 on your own, and then turn it back on when you're ready to hear the answers. All right, hopefully you paused it. But the square root of negative 100 is the square root of negative 1 times 100. Square root of negative 1 times square root of 100 is I times 10, or 10I. Square root of negative 32, I'm thinking, that is square root of negative 1 times, you may think of 4 times 8, or you may think of 16 times 2. Both 4 and 16 are perfect squares. I'm going to go with the larger because it will reduce this square root as far as it can reduce. So 16 times 2. That's square root of negative 1 times square root of 16 times square root of 2. That's I times 4 times square root of 2. So 4I square roots of 2, or 4 square roots of 2I. Either one. Last one, square root of 50. Square root of negative 1 times 25 times 2, which is square root of negative 1 times square root of 25 times square root of 2. The first reduced to I times 5 times square root of 2. So it's 5 square roots of 2I, or 5I square roots of 2. Either one is fine. All right, that was square roots. Now we are moving into adding and subtracting pure imaginary numbers, a part of learning target 6. And again, if it feels right, if it feels like that's what you should do for an algebra with an x, it's probably what you should do here. So 2I plus 6I. If those were x's, you'd have no hesitation. You'd say 8x. So if it feels right, it's probably right. 2I plus 6I becomes 8I. Subtracting imaginary units, 12I minus 5I. If it feels right, it's probably right. 12I minus 5I is 7I. Negative 15I plus 11I is negative 4I. All right? Now we have some square roots. So again, if there's a square root involved, you're going to use the fact that I equals the square root of negative 1, and you should always use that fact first. So the square root of negative 9 is the square root of negative 1 times 9. It's square root of negative 1 is I. Square root of 9 is 3. It's 3I. The square root of negative 100 is square root of negative 1 times 100. So it's I times the square root of 100. That's 10. So it's I times 10, 10I. So far, we've just used what we did on the previous page. But now, if it feels right, it's what you should do. 3x times 10x would be 30. x squared. So in this case, it's I squared. But remember, I squared was the second fact on the first, on that second page where we introduced the 3 facts for today. So if I squared is -1, if it ever shows up, you can use it. I squared can be replaced with -1. So the answer to this question, -30. E, if it feels right, it's probably right. What do you do to multiply -5i times 3i? -5x times 3x would be x squared, so this will be -15i squared. And anytime you see an I squared, it can be replaced with -1. So -15 times -1, +15. All right, last one, f I squared. Again, if you see it, it can be replaced. -1 times I becomes -I. All right, check your progress. Pause the video again. Take a second. Try these 3 if you need to rewind it, or if you need to scroll up and see what we just did. Try those 3. All right, hopefully you paused it. The square root of -49. The negative, I'm going to start poking the I out. I'm going to, in my mind, just see, all right, if it's negative, then it's going to have an I on the outside. And the square root of 49 is 7. So that's 7I. Times, let's see, I'm going to poke the I out, and the square root of 121 is 11, so I times 11 becomes 11I. So when you multiply 7I times 11I, you get 77I squared, and again, I squared is -1, so we replace that, and your final answer is -77. 12I times 3I is 36I squared, and again, you can replace I squared with the fact of -1, with it being -1. So your final answer is -36. All right, the last one's kind of tricky, and it can be done several ways. But I squared, it's not a square root, so we're not going to be using the square root of -1 fact. We're going to be using the I squared fact. So how many I squareds can you make out of 7 I's? Well, just for the illustration of this video, I'll do it the long way. This I probably wouldn't really do, but I can make 1 I squared with the first 2 I's. I can make a second I squared with the second 2 I's, and I can make a third I squared with those 2 I's, and I still have a leftover I, which means when I replace those with -1s, I have 3 -1s being multiplied, and then an I being multiplied. So -1 times -1 makes +1, times the third -1 makes -1 times I, or -I. All right, there's definitely other ways to do that problem, and we'll see those in the homework. Moving on. All right, now we experience the Bell-work problem where we use the square root property. So this time, when we subtract 256 to solve this, we get 4x squared equals -256, and then we divide by 4, so -256 divided by 4 is -64. We'll notice that x squared is now equaling a -64. To solve for x, we have to take the square root of both sides, and there comes the square root of a negative. So x equals, don't forget that there's a positive or a negative answer, plus or minus. Again, that's back to the Bell work. Plus or minus answer, square root of -64. And I'll remind you that the square root of -64 is the square root of -1 times 64, which is I times 8, or just 8I. So your answer here, x equals plus or minus 8I. 2 pure imaginary answers to that quadratic. Whew, I know we're moving fast, trying to get this all done in one video, so keep going. All right, this is kind of like that match game in the newspaper where it's the same on one side of the equals as it is on the other side. But what it really is a plus bi equals a plus bi. If you have two complex numbers like we do in this situation, the 3x minus 5 represents a, whereas on the right side the 7 represents a. So what that means is if they're supposed to be equal, which the problem says they are, then 3x minus 5 will equal 7. Furthermore, the y minus 3i is the imaginary part, b, the imaginary part bi, and it must equal the imaginary part bi on the right side. So the y minus 3i must equal 6i, so the y minus 3 has to be 6. So the x and y that makes this true is, add 5 to both sides, 3x equals 12, the x is 4, and the y is, add 3, the y is 9. So the x is 4 and the y is 9. It's kind of like that match game from the newspaper. You have a complex number on the left side of the equation and a complex number on the right side. So the real parts must be equal, 3x minus 5 and 7, and the imaginary parts must be equal. All right, I know I'm going really fast. You may have to rewind this and whatnot. But now learning target 7 jumps in, and we're adding and subtracting and multiplying complex numbers. Again, if it feels right, it's probably what you should do. So when you're adding, you just add like terms. 5 minus 7i plus 2 plus 4i. Your like terms are 5 and 2, so they make 7. And the imaginary terms, negative 7i and positive 4i, makes minus 3i. So when you add complex numbers, you get a complex number. When you subtract them, you got to be careful and make sure you subtract the 3, so minus 3, and you subtract the negative 6, which turns into plus 6i. So combine your like terms. 4 minus 3 becomes 1. Negative 8i and positive 6i makes negative 2i. And so when you subtract complex numbers, you get a complex number. What happens when you multiply complex numbers? If it feels right, it's probably what you should do. First, outer, inner, last, you're going to multiply 2 times 5 and 2 times negative 6i. Then you're going to multiply 3i times 5 and 3i times negative 6i and combine your like terms. So 2 times 5, the f is 10. 2 times negative 6i is negative 12i, so plus a negative 12. I'll go ahead and erase the plus because it's just going to be minus 12i. Now the 3i times 5, the inner, 3i times 5 is positive 15i. And then the last, 3i times negative 6i is negative 18i squared. Be careful on that last one. It's I times I, so it's I squared. All right, sorry about that, Bill. Our middle terms combine to make 3i. And then we notice an I squared showed up in the work. So we can change that I squared to negative 1. So we have 10 plus 3i. Negative 18 times negative 1 is plus 18. And we have a like term of 10 and 18. So 28 plus 3i. Whoops, plus 3i. So, moral of the story, what happened when you added complex numbers, subtracted them, or multiplied them? You get a complex number as your answer in all 3 of them. So, what's going to happen, do you think, what do you think, is going to happen when you divide them? When you divide them, you're going to get the same thing. And I tell you what, this video has become already too long. I'm going to stop it where it's at and save this as everything but division, and then I'll post the other video with division, which is probably what I'm going to end up teaching on Friday anyway. I'm teaching on day 2 of this lesson.